Salts are ionic compounds. Yeah, in your notes, you got to get that kind of stuff cleared up. Otherwise, when it comes time for the exam, then there's confusion.
Wasn't it something like a cation and an ion combined together? No.
Well, the way I defined it is the salts are just ionic compounds that are not acids. And so anyway, salt crystals are just would form here. Lead-2 nitrate's white, so we form white crystals at the bottom once all the water is evaporated. Same thing here. These magnesium and iodides stay apart. They're dissociated in solution. They don't come together. So, we wouldn't consider these favorable ion combinations. It's favorable in the sense that once the water is gone, then we can form solid magnesium iodide, which is a salt. The same thing with lead-2 nitrate. But the bonds that are holding the ions together aren't super strong, so that water can dissociate it. I mean, they are strong because lead-2 nitrate and magnesium iodide do have fairly high melting points. So what happens is when we mix these together, we're going to get a whole bunch of ions mixed together. And so the ions that we're going to get mixed together now are going to be lead, magnesium. We're going to have the iodides and the nitrates. They're going to be moving about here. Then we look, are there any favorable ion combinations here? Do any of these ions really come together and react? In that sense. Yeah. Lead and iodide like each other a lot. And so the lead and iodide are going to come together. In fact, the lead comes together with two iodides, and it's going to form a solid. And the solid is going to sink to the bottom eventually, but it'll probably be a cloudy precipitate, what we call. And so we get a precipitate of PbI2 solid because iodides, when combined with lead ions, are insoluble. And so this is a favorable ion combination here. All right. However, a lot of people like patterns. They want patterns. And one of the patterns that is really common is the AB plus CD pattern. Your book doesn't do it. Your book does AX plus CY. Maybe I should do the same as your book.
That makes more sense.
I like
Makes more
ABCD.
sense. It makes more
All right.
Yeah.
AB plus CD. AB plus CD, what we do is we just switch the anions here. This is called a double replacement reaction. We switch the anions here. So then we pair up the lead ions with the iodide ions. When we pair that up, we get lead-2 iodide, which has the formula PbI2. And then we pair up the magnesium ions with the nitrate ions. So we'll end up with MgNO3 And then we say, is this a favorable ion combination? Yes, this results in a precipitate. Is this a favorable ion combination? It's not going to precipitate, and so no, but it's there. This is the remaining ion combination because once the iodides are taken up by the lead, then what's left over? Magnesium and nitrate, and if I evaporate all the water, the magnesium nitrate will come out as well. And so this is aqueous here. And so what we have is what we call a driving force for this. Use this. The reason I call this, why don't I just call this double replacement? The reason I don't call it double replacement is because people get into the mentality that it's got to be AB plus CD pattern. And so on a test, I might throw, not in Chem 4, but in Chem 1A, I'll throw in this, AB plus CD plus EF. I'll throw in an AB plus, BC, whatever, plus EF, and people can't do it. People can't do it because all of a sudden it doesn't fit their pattern. And if it doesn't fit their pattern, then they've never seen it before. If they've never seen it before, it's not a fair question, right? Because, hey, that's not fair. I've never seen that before. And so I've been trying to get away from that because people box themselves into a tiny, tiny box. And all they can do is, what's inside that box. So You know, EF is just another ion, so throw 2 more ions in the mixture. If you throw 2 more ions in the mixture and then look which ones are going to be a favorable ion combination, it doesn't matter how many. I could throw in 10 different compounds in there, and you're just looking for favorable ion combinations. And so if I went on GH, etc., and threw in this wild mixture of compounds and asked you, okay, what's going to happen? You know, some people might,
How do you know what's favorable? Like, how do you know which ions are going to want to get together?
Well, that's it. What's favorable is precipitates are favorable, right? So how do you know? You memorize the solubility rules, for one. Precipitates are favorable because the ions come together and actually react in solution and drop out. That's favorable. But there are other things that are favorable too. I just started off with precipitates. There's more. There's more, but I didn't want to talk about it just yet, but I'm going to talk about it now. And so what is favorable? What is a favorable ion combination? Favorable ion combination is going to be what we call a driving force for a reaction. And so what are all the favorable ion combinations? All the favorable ion combinations are one, if a precipitate forms. If a precipitate forms, then great. That's a favorable ion combination because those ions are going to drop out of solution. And so we need to know the solubility rules for that. You have to memorize those, fortunately. 2, there are other favorable ion combinations that, and there's some overlap here, but one of the other favorable ion combinations is this. If we go from a stronger acid is a strong electrolyte, or a stronger electrolyte. If we go from a stronger acid to a weaker acid, that's a favorable ion combination because in a weaker acid, the hydrogen ion, the proton's held more tightly. In a weaker acids are more stable, less reactive. And so here, the H, let's say, example would be, let's say on the left side we call the reactant side. We have HCl. On the product side, or the right side, let's say right side, is the product side. Let's say we form acetic acid. So if on the left we have hydrochloric, and then we're going on the right, we have something like acetic acid as a product, you know, through this reaction mixture, this is a much more favorable ion combination. So if there are hydrogen ions on the left, those hydrogen ions like acetate ions. And so the hydrogen ions will attack acetate ions. When they attack acetate ions, it forms a more stable product versus hydrogen ions attacking chloride ions. If hydrogen ions attack chloride ions, nothing happens because they stay apart. HCl is a strong electrolyte. Strong electrolytes are totally dissociated in water, right? But weak electrolytes are not. Weak electrolytes are partially dissociated in water, and so if hydrogen ions attack acetate, or chemists don't usually think this way. Chemists usually think the base attacks the acid. So acetate attacks hydrogen ions, we form a more favorable acetic acid. Does that make sense? And so if acetate's present, and we have chloride present, then acetate's going to attack the hydrogen. It's a form a more stable product. This is a lot less reactive. And so this is what we call stronger acid to weaker acid. It doesn't have to be a strong acid. It need not be HCl. It just has to be stronger than this. And so we can go from something like phosphoric acid to water. You know, that would be stronger acid to weaker acid, although phosphoric acid is considered weak acid. All right, and then 3, there are some things that form gases or decomposition. Your book calls it decomposition. Your book calls this formation of water or weak electrolyte. Gas formation would be like this. You know, hydrogen ions like carbonate ions. And so if we have hydrogen ions and carbonate ions, then what's going to happen are these are going to combine to form H2CO3. Actually, we'll need 2 hydrogen ions for this. H2CO3, however, is not stable. This is unstable and immediately decomposes into H2O liquid plus CO2 gas. And so this results in effervescence or bubbling. And so hydrogen ions, like carbonate ions, hydrogen ions like the stronger bases than chloride. Could be acid base as well. Okay, this could be acid base as well, so there's a little bit of overlap, so this is why I concentrate on precipitation first. That's what we look for first. Not four. Let's. What else does hydrogen ions like? Hydrogen ions also like, this is also stronger acid to weaker acid, so there's a bit of overlap. Hydrogen ions also like sulfite ions, SO3 2 minus. We have two of those, that forms H2SO3. H2SO3, sulfurous acid is inherently unstable too. Sulfurous acid breaks down into sulfur dioxide and H2O. Sulfur dioxide is a gas, or can be a gas. And hydrogen ions also like, any other base. But any other base is going to be classified as this over here. So we'll eliminate that. There's one more that's unstable, and that's ammonium ions. Ammonium ions is another acid. Ammonium ions like hydroxide ions. Ammonium ions like hydroxide ions to form ammonium hydroxide. Ammonium hydroxide, however, is not so stable. Ammonium hydroxide decomposes. When ammonium hydroxide decomposes, it decomposes into ammonia and water. The ammonia can be aqueous or gas, depending on the temperature. Ammonia is very soluble in water because ammonia is very water-like. And so it's quite soluble. So these are the ion combinations. That's all of them right there. So you have to memorize those as potential ion combinations. Now, what we're going to do is we're going to break down these reactions to look just at that favorable ion combination. And so the first equation I wrote here is what we call the complete equation. The complete equation, CE, was the PbNO3, actually I shouldn't erase it, PbNO3 2 AQ plus MgNO3 2 AQ yields PbI2 solid plus MgNO3 2 aqueous. Okay, then we have the ionic equation. The ionic equation are what are the major species in solution. What I mean by major species is this. The major species, if it's a strong electrolyte, the major species will be the ions. If it's not a strong electrolyte, the major species will be just whatever we have. And so what we come up with something called the ionic equation. The ionic equation just says ionize the strong electrolytes. We already did it, but we'll do it again for practice. Lead-2 nitrate, is it a strong acid? Is it a strong base? Is it a soluble salt? It's a soluble salt, so we ionize it. We ionize it into Pb2 plus 2 nitrates. So for every lead, we have 2 nitrates. Then we go to magnesium nitrate. Magnesium nitrate, is it a strong acid? No. Is it a strong base? No. Is it a soluble salt? Yes, it's a soluble salt. So this is going to break up into magnesium 2 plus 2 nitrates. Lead iodide, is it a strong acid? Lead-2 iodide, no. Is it a strong base? No. Is it a soluble salt? No. So leave it alone. Magnesium nitrate, strong acid? No. Strong base? No. Soluble salt? Yes. So we break it apart. And so what we have here is compare this with what I have written for the beakers. This is just the major species that we find inside the beakers. All right, now what we have is we have something called the net ionic equation. The net ionic equation wants to just focus in on the favorable ion combination. And so what we're going to do is, for example, this. We're going to eliminate the ions that didn't react. Like nitrate. Did nitrate do anything? Sorry, this is iodide. Magnesium iodide. We got too many nitrates. So that should be iodide. 2 iodides. Did nitrate do anything? Did nitrate react with any other ions? Was there a favorable ion combination for nitrate? Look inside the beakers. No. Nitrate stayed in solution the whole time. It didn't react with anything, did it? And if it didn't react with anything, we call it a spectator. So nitrate's a spectator. Are there any other spectators? Magnesium ions are also spectators. Good. And so we have spectators here. These spectators, since they don't really react, we just want to focus on the favorable ion combination. The favorable ion combination is going to be lead, 2 ions with iodides. This is the favorable ion combination, and that's going to form PbI2. And so I call these metathesis the favorable ion combinations because it doesn't matter what the pattern is. We're just looking for ions that like each other. That's all. And so I could have any kind of bizarre mixture and just look for ions that like each other. That's it. Let's do one more here. Uh-huh.
The equation, so we have to keep putting the state up, or just worry about the solid and not putting?
Okay, that's a good question. You know, eventually you start getting tired of writing AQ all the time. It's very common, AQ, AQ, AQ. And so we have 2 options here. One, we write AQ all the time. Or 2, we leave off AQ but write everything else, which would be solid, liquid, gas. So if there's a solid, liquid, gas, you can just write those and assume everything else is AQ. And so you have 2 options here. Some people want to write it each time, and that's fine. You could write it each time like this. Other people don't write anything. If you don't write anything, then that's a problem, because then I'm going to deduct, because I'm going to assume you know nothing about the states. But if you don't write the aqueous states and you write all the non-aqueous states, then I'm going to assume you know it. You just don't want to write AQ over and over and over again. Okay? And so it's up to you, but whatever you do, you have to be consistent. And don't write nothing. And so what I'm going to do from now on is I'm going to use this, because I don't want to write AQ all the time. And so if it's not written, we assume it's aqueous. And so we're going to go with the next one here. The next one example is going to be, let's see, we'll do, okay, we're going to do ammonium carbonate and HCl, hydrochloric acid solutions, are mixed. Now, when you see the word solutions, it's automatically aqueous. You know, solutions means AQ. And so if I combine these 2 solutions, what do you expect to happen? And so let's take a look. Ammonium carbonate, what's the formula for ammonium carbonate? NH4, 2, CO3, good. That's good. Is ammonium carbonate soluble? Yeah, all ammonium salts are soluble, so it's aqueous. Is it a strong acid? Strong base? No, NH4 is a weak acid. NH2 minus, you must be thinking NH2 minus, which is called amide, is a strong, powerful base. Is it a soluble salt?
Yeah.
Yes. It's soluble. Ammonium salts are soluble. So when I look at a solution like this, I visualize ammonium ions and carbonate ions moving about in solution, dissociated. These are free. This is what I visualize. I see that. Okay, hydrochloric acid, HCl. Soluble?
Yeah.
Yes. So I said I'm not going to write AQ, but I'm writing AQ. But I could leave it off.
For those that don't break down, like lead to iodide, they're always going to be solids?
No.
No.
No, we also have liquids and we have gases. So for example, if you make CO2 gas, is CO2 gas a strong acid? No. Is it a strong base? No. Is it a soluble salt? No. Then leave it alone. It doesn't break apart. Strong acids, strong bases, and soluble salts break apart. They break apart or they do something called strong bases don't dissociate, or in fact all bases don't dissociate. Bases, instead of dissociating, what do bases do? It starts with an H. Hydrolyze. Yeah, bases hydrolyze. Well, HCl is a strong acid, so that's going to dissociate. Acids do dissociate into H plus and Cl minus. The H plus I'm going to put in quotation marks here because H plus is very unstable. H plus has an extremely high charge density. In other words, an extremely high charge to size ratio, which makes it very reactive electrically. And so it's too reactive to exist stably in water. And so when I see H plus, in reality, it's what? Hydronium. Yeah. But you know what? Hydronium is a bit of a hassle to write out, just like AQ. And so, just like chemists will assume, oh, that's aqueous, because they know, hey. People are assumed to know, yeah, H plus, that's going to be hydronium. Same kind of deal. All right, so these are the ion mixtures. So this is, this is going to be a metathesis reaction. We're mixing up ions. This is the first thing we look for is metathesis because we've got ions mixed together. And so we're going to look for a metathesis reaction. But what we're going to do is we're going to follow the pattern. The pattern is going to be AB plus CD. AB plus CD yields AC plus BD. And so if you want the pattern, that's going to be ammonium with chloride. Ammonium with chloride is, what's the formula for that? NH4 Cl. Now, what do? I have two ammoniums and one chloride, so it's not quite balanced. But I don't worry about the balance. I just worry about getting the formula right. So if I have ammoniums and chloride, this is how they're going to combine in a 1-to-1 ratio. That's going to leave one of these ammoniums unpaired, but that's easy to fix. I just add some more HCl to this. Now, BD is going to be hydrogen ions with carbonate. Hydrogen ions with carbonate is going to form what? And so I have a carbonate here, and I got a hydrogen ion here, but I don't have enough hydrogen ions. But that's easy fix because I just add some more HCl, and then I have enough. It's going to be H2CO3, carbonic acid. And so the easy fix is this. I just increase the HCl to 2 HCl's. I'll increase this to 2 ammonium chlorides, and then this works out. And so now this is what we call balanced. Yeah. But I got to see, is there a driving force? Is this a precipitate? No. Is this a precipitate? No. And so neither of those are precipitates, so I worry. Maybe there's no driving force for this. If there's no driving force, that is, if we can't find a favorable ion combination, then nothing's going to happen. There's going to be no reaction. The ions are just going to sit there, right? We got to find a favorable ion combination. Was there? Oh, in fact, there is. One favorable ion combination is we're going from a HCl is a strong acid to a much weaker acid. Is carbonic acid considered one of the 7 strong acids? No. So we're going from stronger acid to weaker acid. But there's something else that's happening here. And so we're going from stronger acid to weaker acid. We call that driving force. Because do weak acids dissociate into ions? No, the weak acids stay together. We only dissociate the strong acids, strong bases, and, well, strong bases we hydrolyze, and soluble salt. Weak acids stay together. That means that the ion combination is good, right? If the ions stay together, then the ion combination is good, making it less reactive. So, but there's a problem with carbonic acid. You have to have this memorized. Carbonic acid is unstable. And so carbonic acid shouldn't be a product because it's unstable. It's going to decompose into water and carbon dioxide. Carbon dioxide is a gas. Carbon dioxide is also known as a Lewis acid. But Lewis acids I'm skipping for this. And so we're still going from stronger acid to weaker acid. The weaker acid in this case is CO2, which is an acid. It just behaves a little differently than the Bronsted acid. There are other Lewis acids out there as well that are important, but this is it. And so what we also have is effervescence or gas formation. Gas formation is another driving force. You know, as the bubbles of gas form, it will drive this reaction forward. And so we're going from stronger acid to weaker acid, and we have gas formation. So this is a favorable reaction. The ion combination works out well. The hydrogen ions and the carbonate ions will bump this up to 2 hydrogens and 2 chlorides. The hydrogen ions and the carbonate ions like each other. They react, and that decomposes into water and CO2. So this is what we call the complete equation with driving force. We need the driving force. The driving force over here was precipitation. Okay, then what we want to do is we want to get something called the ionic equation. The ionic equation is just, all you do is you dissociate the strong electrolyte. And so when we do that, we got 2 ammoniums here, plus a carbonate in this beaker. And over here we're going to have 2 hydrogen ions and 2 chloride ions. And then ammonium chloride, is that a strong acid? No. Is it a strong base? No. Is it a soluble salt? Yes. So we dissociate that. We get 2 ammoniums and 2 chlorides. You got to be careful because a lot of people make a mistake. They get 2 ammoniums and 1 chloride. You can't have 2 ammoniums and 1 chloride. It doesn't balance out. You're going to have 2 ammoniums and 2 chlorides. Then it's balanced out. Is water a strong acid? No. Strong base? No. Soluble salt? No. Therefore, leave it alone. Is CO2 a strong acid? No. Strong base? No. Soluble salt? No. Leave it alone. And so what we're going to end up with in this beaker is this. We're going to end up with ammonium ions, this, 2 of them, chloride ions, and then what's going to happen to the CO2? The CO2 is going to bubble out as a gas.
Why would we not just leave it as carbonic acid and then instead of separating it into water and CO2? Is it because it's so unstable that it's just good?
It's so unstable, it happens immediately. Immediately as it's formed. If we could isolate carbonic acid and trap it, yeah, then maybe we could do that. But, you know, each one of these equations is standalone. And so it's not like a time sequence. The first second, it's this. The second sentence is this. the second, it's this. You know, all three of these have to be valid at the same time. And so if you left it at carbonic acid in the first equation and wrote it as CO2 and water in the second equation, that's wrong. You know, because there's no time. This is not a sequence in time. You know, this is just one snapshot in time, and it's the same time. All right, if we look at the ammonium ions, they're over here. And the ammonium ions stay over here in solution. So did anything happen to the ammoniums? No. This is a spectator. How about the carbonates? Did anything happen to the carbonates? Yes, they combined with the H+. So the ammonium is a spectator. H+ reacts. Chloride, does chloride react? No, so chloride. So the spectators are ammonium and chloride. And so in the net ionic equation, the NIE we call it, net ionic equation, which just means what was the favorable ion combination? The favorable ion combination is two H pluses and a carbonate. The H plus and carbonate like each other, and they're going to form H2O liquid plus CO2 gas. That would be the net ionic equation. So those are some examples of metathesis. Now, is metathesis the only type of reaction that can occur? No, there are two more. Acid-base. Well, when we look at this, this is the same. If we did the acid-base, we get the same result because carbonate is a base, H plus is an acid, so this is acid-base and metathesis. Overlaps. And so that takes care of metathesis and acid-base. And what's the final one? Redox. Now, these can undergo redox reactions. H plus is what we call an oxidizer. Chloride's a reducer. H plus is what we call a moderate oxidizer. Chloride is chlorine would be a strong oxidizer. Chloride would be extremely weak. And chloride's so weak we don't really consider it much, but it could. Ammonium, reducer, but we need a strong oxidizer, much stronger than H plus. Carbonate, if you were to guess, because carbonate's not on the chart, if you were to guess carbonate's properties, would you consider it more of an oxidizer or more of a reducer? Or maybe in between? I would consider carbonate more of an oxidizer. Why? No, because I always look. Well, the first thing you look at when you're looking at redox properties is to determine the oxidation state or oxidation number. Oxidation states and oxidation numbers are key to understanding redox. But the thing is, the numbers are just the numbers. A lot of people will go, "Oh, great! I can calculate it. I can calculate the oxidation state or oxidation number because I memorized the rules." But there's a major problem with that, and the major problem is that that's not the challenge in science. To be able to use some mathematical equation to calculate an oxidation number, anybody can do that. Anybody with no scientific background can do that. The difficult thing is to interpret the numbers. So, for example, a 0 on fluorine versus a +2 on magnesium. A 0 on fluorine versus a +2 on magnesium, which one's more electron poor? Fluorine with a 0 charge or magnesium with a 2+ charge, which one's more electron poor? No, fluorine. Fluorine. How? Because you have to associate, properties with numbers. Because why do I know fluorine? Well, it's not coming up right now, but there's a bit of memorization you have to do. For example, what is the most electron poor species on the chart? On the redox chart. Unfortunately, something's wrong with the computer right now. I can bring up the redox chart. But did anybody print out the redox chart? Okay, at the top of the chart is fluorine. Fluorine with a 0 charge. At the bottom of the chart is lithium ion. Lithium ion is what we call the worst oxidizer. Worst oxidizer means it doesn't really want electrons that badly. It means it's not that electron poor. This one is extremely electron poor. H plus is kind of in the middle. But magnesium, do you know where magnesium ion is? Is it up here towards fluorine or down here towards lithium ion? It's down here towards lithium ion, which means that magnesium isn't that electron poor. In fact, magnesium metal is what we consider electron rich. Magnesium metal is electron rich. Fluorine being electron poor means fluoride is not electron rich. Fluoride is not what we consider electron rich.
Is it because it's based on the structure of the atom that it's considered like magnesium metal, for example?
Right, based on the structure of the atom. Not just the atom, because if you look at a single atom, it's based on the structure of the crystal. When you look at a metal crystal, what happens is you have what they call and we'll talk about this when we get to bonding, but you have something called the electron sea model. And so metals are thought to be like a sea of electrons. And this is why metals are thought to conduct electricity so easily. You know, metals conduct electricity so easily because you got this ocean of electrons in metals. And since there's so many electrons in metals, they're considered electron rich. All metals are considered electron rich. This is why metals are considered highly flammable. In fact, we're going to look at magnesium right now because I got some magnesium here. If you look at magnesium, it looks like a typical metal here, you know. But magnesium is kind of a soft metal. It's a light metal, and structurally it's pretty good, right? But metals are electron rich. And so what that means is electron-rich substances are what we call fuels. And so what we do is, how do you know this stuff, is you memorize and associate certain things. And so that's the hard part. That's what we call specialized knowledge, you know, or the stuff that you can't necessarily get a computer program to do easily. You know, you can't just program something in BASIC and have it figure this stuff out because it's a lot more complex. You'd need a higher level of artificial intelligence in a computer to do that. Well, that's what we got to do. We got to do these interpretations ourselves. And so the first thing to do is I told you that the chemistry has a two-pronged approach. is way too hard to figure this out, you know, and so a lot of this stuff is just determined by experimental measurements. So if I take a piece of magnesium like this and then we'll just put it in the flame. Let me get a large beaker. And so what we do is we make an association. Well, how electron rich is magnesium? And so I'm just going to use this to capture any smoke that might be generated in case I don't want to set off the fire alarm. But do you see this burn? That's smoke. Do you know what that smoke is? I'll talk about the smoke here. Well, that's reacting with oxygen. Oxygen is an oxidizer, you know, and so this is magnesium that's burnt. And so magnesium is, well, how electron rich is it? It's that electron rich. Did you see how well that burned? Iron does the same thing. Do I have some iron? I'll bring in some iron. But iron's not going to be nearly as electron rich as magnesium. Sodium would be much worse. You know, sodium is considered. How do I know? Because I know based on certain things. Like if you look at the pattern, did you guys see any kind of pattern to this? It depends on how many times you look at this. The pattern is that the group 1 metals are the most electron rich. Did you notice that? Followed by the group 2 metals. These are patterns you see when you start looking at it. Not just once, but you got to look at it many times and then the patterns stick out. But unfortunately, this is what they call descriptive chemistry. Descriptive chemistry's fallen out of favor because nobody likes to memorize things, but unfortunately, that's the only way you can do it. And so a lot of people, they have no idea how magnesium will react or what magnesium is unless they Google it or something like that, you know? But that's not the way we want to be, because then we don't have any specialized knowledge for this. We want this specialized knowledge. Now, what is this white stuff? The smoke that deposited here is the product of the combustion. What do you guess that is? Well, what we guess that is we look at the reactants. So we're going to switch gears here and go to going to redox, right? And so magnesium is very reactive. That means its conjugate is very unreactive. So if magnesium is reactive, magnesium ion is very unreactive. So magnesium ion is not really considered much of an oxidizer. And so getting back to this, I don't expect much redox to occur, because this carbonate, you know, I asked you what do you think carbonate is? An oxidizer or reducer? Carbonate is you'd expect it to be an oxidizer, because what do we know about the oxidation states? Well, what you should know is that an oxygen in the -2 is nothing special. What we do is we make these little associations. So for example, water is a reference compound. We need little reference compounds to keep things in track. And so fluorine is one of the reference compounds that we keep in track, because fluorine is the most powerful. In fact, you know, the way you remember fluorine, you know, fluorine chemist's handshake. Fluorine will catch stainless steel on fire. If I put a chunk of stainless steel in the flame, is it going to erupt into a flame like that? No. If I put a piece of stainless steel and nothing happens. I got some stainless steel here. You know, I put this stainless. Actually, is this stainless? Maybe not. I put this stainless steel in the fire. It just gets hot. It's not going to burn. And so water is another reference. Water is another reference compound because water is stable. You know, it's not really acidic, it's not really basic, although it can act as an acid, it can act as a base. It can also act as an oxidizer, and it can act as a reducer, but it's not very reactive. And let's look at the oxidation states. Well, hydrogen is +1, oxygen is -2. That must mean that hydrogen's fine at +1, oxygen is fine at -2. And so I don't think of that as being especially unusual. So if I were to ask you, is this electron rich? Not really. You know, it's happy as is. Happy as is. Now, of course, this is not easy because this is like I said, 30 years or whatever, probably more than 30 years of observations, you know, crammed into a little table like this and other stuff. But the advantage is you don't have to reinvent the wheel. You don't have to go through 30 years to understand this. So science is built up like technology, you know. The way it progresses is you build up on existing knowledge. And so here, water is pretty stable. Now let's look at some redox here next. Magnesium solid, is that electron rich compared to O2 minus? Or is O2, which one's more electron rich, O2 minus or magnesium solid? Magnesium solid. How do you know? You've memorized certain reference points, you know, that you can do. And so this is how you know. You know by association. This is what we call descriptive chemistry. Now, sorry, I have to turn this on. Now, the theory of chemistry is what we call quantum mechanics. Quantum mechanics, we should be able to figure this out. But do you know the calculations in quantum mechanics, the mathematical calculations, are so difficult that they have to use what's called approximations. They have to guess at certain things when they try to solve the math. You can't come up with, in math you want the right answer. What is the right answer? The right answer is the number that you get from the calculation. In quantum mechanics, you can't get the right answer. What you have to do is you have to make approximations to get something close to the right answer. How close? Well, it depends on how much you want to wait, and you know, and how difficult the calculations are. And so we don't use theory. A lot of chemistry is just descriptive. Descriptive chemistry means you have to memorize stuff. And memorizing stuff takes time, of course, and this is why some math people and some physics people hate chemistry. They hate chemistry because of this memorization stuff. They just much rather have an equation, plug in the numbers into the equation, get out the answer. It's a lot easier. Until the math gets really hard. Okay, well anyway, let's go on with this. Yeah, magnesium is much more electron rich than oxide. Much more. Metals are electron rich. Group 1 metals are the most. Group 2 are the next most. Then we have the coinage metals, like silver. Do you consider silver very electron rich? Silver, gold, platinum. Is silver, gold, platinum, and even copper to some extent, are those really electron rich? No, those aren't. If you look at the position of silver, silver is very far away from lithium metal. Silver is way up here. Silver is very hard to oxidize. Gold's not on our chart, but gold is even harder to oxidize, yeah.
Like as you go left to right on the chart, it goes like electron rich all the way down to electron 4.
Yes.
Towards the end, it's electron.
Right. When we look at the periodic table, it's exactly the most electron-rich species is the biggest. The most electron-rich species is the cesium. However, our chart doesn't show it. Our chart shows lithium. We predict cesium to be the easiest to strip an electron off of because it's the biggest atom, and so the biggest atom should be the easiest to take an electron from. It is lithium, not because it's easy to take an electron off lithium, it's because of the stability of the product. Lithium forms lithium ions. Lithium ions like water. And so there's other reasons for that. But I mean, for the most part, there are going to be questions. When people really look at that chart, questions pop up. Like, for example, okay, sodium versus potassium. Potassium's better. And so that makes sense. Potassium's bigger than sodium. But when you go down to lithium, lithium's smallest of all. Why is lithium at the And so that's the first question that comes up. People, and these types of questions get asked. So you use the chart, and then somebody asks you a question. Somebody asks you a question, hey, why is lithium the most electron rich? Doesn't quite make sense because lithium is a smaller atom. Smaller atoms, why is helium smaller than hydrogen? Somebody tell me why helium is smaller than hydrogen. Well, helium has 2 protons. Well, so it pulls in the electrons closer. So smaller atoms, the nucleus pulls in the electrons closer, meaning there's stronger attraction for the electrons. Bigger atoms, the nucleus doesn't pull in the electrons as close. So bigger atoms should be easier to ionize. And so it's totally wrong. So the question that you may get asked is why? But you might not be prepared for that because if you don't even know the chart, then you won't be able to answer. It'll catch you off guard, and that happens. That happens in science. A lot of people get caught off guard. They get caught by questions that totally throw them off. So you'd have to think about it for a while. But anyway, yeah, the most electrons, that's the pattern. You see the pattern? The pattern in this chart, you can see it in the periodic table. The metals to the left are more electron rich than the metals to the right, for sure. And eventually, they don't even call them metals anymore. Like when we start getting here, even aluminum, when we start getting here, we start to transition from metals to non-metals. And that transition zone is called the semi-metals or the metalloids. And so the semi-metals and metalloids have properties intermediate between metal and non-metal. And so the pattern here is you go from the most metallic on the left. Most metallic are, what defines a metal? All metals are electron rich. All metals conduct electricity. All metals lose electrons in undergoing chemical reactions. So those are the properties of metals. Anyway, we'll go back to this here and we'll talk. So magnesium, metathesis. Are there any metathesis properties for magnesium metal? We're going to just go through all 3 reactions, not just redox. But let's first start off with metathesis. Magnesium metal, metathesis? Will magnesium metal participate in metathesis reactions? No. Why? Because it's not an ion. Metathesis requires an ion. Magnesium is not an ion. It's a neutral element. It's a metal. And I talked about Dr. Jekyll and Mr. Hyde, right? The magnesium would be the Mr. Hyde. Dr. Jekyll would be the magnesium ion. Magnesium ion is stable. Magnesium metal is unstable. You can see. In fact, okay, and then acid base. Is magnesium a good proton H plus donor? There's no H. Right? It's not an acid. Is it a base? It's not a Bronsted acid base, but it is it's a Lewis. But we're skipping Lewis because Lewis is too difficult to discuss in a short period of time. You need a lot more time to talk about Lewis. And so keep that in the back of your mind. When we do acid base, we're missing a category of acid bases, like CO2. CO2 is very common Lewis acid and undergoes a lot of Lewis acid base reactions, but we aren't going to get into it because we're skipping Lewis acid bases due to time constraints. If we have plenty of time, it's fine. It's no problem. CO2 is easy to talk about. And so there's no metathesis, no acid base. That means the only chemical property of magnesium is redox. Now where is it? Is it on the oxidizer side or is it on the reducer side? It's on the reducer side. Is it a strong, moderate, or weak reducer? It's a strong reducer. So automatically I think that this is a strong reducer. Now, a strong reducer should react with, well, it doesn't have to be strong. It just has to be strong enough, right? And so what is strong enough? Strong enough is this. Strong enough, I've got to line this up. Magnesium metal will be oxidized by any oxidizer weaker than magnesium 2. So magnesium metal would be oxidized by the weakest oxidizer, lithium ion? Yes or no? No. The next strongest, like potassium ion? No. Magnesium metal needs a bit stronger. Well, how strong? It needs an oxidizer that's stronger than magnesium ion. Any oxidizer stronger than magnesium ion will oxidize magnesium metal. Any oxidizer. Well, let me just do a quick aside here. This quick aside is CO2. Does CO2 have metathesis properties? No, not really. Although it's tricky because of carbonic acid. We don't really think about CO2 because it's molecular. So we don't really think of it in terms of metathesis. Acid base? Not Bronsted. There's no proton donor proton acceptor going on here, but yes, Lewis it does. This is Lewis acid. But Lewis acid we aren't going to get into. This Lewis acid is very important in biology. In biology is, if you don't get enough CO2 out, then you know what happens to your blood pH? Your blood has to maintain a pH. What's the pH of blood? Like 7.2. If your blood pH drops just a little bit, let's say if your blood pH drops to 7.0, you're in big trouble. You're going to have something called acidosis. You're going to be in trouble. One way of that blood pH dropping is the CO2. You're not exhaling enough CO2. You're going to be in trouble. Your blood pH is going to get screwed up. Well, anyway, CO2 is an acid is important, but we're not going to talk about it. We can talk about the redox, though. What do you think? As far as CO2 goes, what would you expect it to be? More of an oxidizer or more of a reducer? Well, oxygen is -2, so maybe it's a reducer. Are oxygens electron rich? No. Carbon is +4. +4, you would probably expect this to be a oxidizer. Now, is it a strong oxidizer like oxygen? No. CO2 is a very weak oxidizer. Is CO2 enough to oxidize wood? Like, can you combust wood in CO2 in an oxygen-free environment? No. CO2 is not enough to combust wood. And therefore, you could use a CO2 fire extinguisher on paper and wood fires, no problem. Because that's going to get rid of the O2. Right? But you never, ever want to use CO2 on a metal fire. If you use CO2 on a metal fire, you're in big trouble. Why? Because CO2 is plenty powerful enough to oxidize most metals. Okay. And so, we just burnt magnesium in air, which is oxygen. We could burn magnesium in pure CO2. I'm not going to do it because you have to buy a block of dry ice to do it, but there's plenty of videos on YouTube of this. And so let's just watch a quick YouTube video. they get it hot initially, but this is block of dry ice. Then they cap it so there's no air. Basically, the CO2 is going to purge out all the air. But do you see the magnesium burning? That's burning without any O2. That's burning in just CO2. So imagine you're spraying CO2 on a metal fire.
What's inside?
That's what it's going to look like. The CO2 is not going to extinguish the metal fire. It's just going to feed the fire. You're fanning the flames for that. And so,
So like when you look at a penny, sometimes that has like.
yeah, pennies.
But my question is, it's not always oxygen. It could be other things as well.
Yeah,
Oh, that's great.
yeah. The green is sulfur. Sulfur, like H2S and sulfates and that. The orange is copper 1. The black is copper 2 oxide for pennies. And so the pennies are going to. Anyway, so the reaction that we just did is this. It's going to be magnesium, not with the CO2 because CO2 is not a very strong oxidizer, so that's why it's not on the list. You know, even though it's a common chemical, it's found in air. It's not very strong. So. But O2 is a strong oxidizer. It's common. And so we're going to have magnesium and O2. Now, how do we figure out what the products of this are? Well, we have to know what they want to do. So, for example, magnesium. And here we're going to use the periodic table to figure it out. But magnesium is going to want to do what? Gain or lose electrons? Lose. And how many is it going to lose? Two. And so it's just a simple pattern off the periodic table. The pattern off the periodic table is, we try to get as many electrons as the noble gases. Noble gases turn out to be very stable, like neon, argon, krypton, xenon. Radon's radioactive, but chemically it's very stable. Nuclear chem-wise, it's unstable. But all these are chemically totally unreactive. It's like gold, gold or platinum. Those are chemically unreactive. Gold, platinum. Even mercury. Mercury's hard to oxidize. Mercury retains its luster, its silver luster, even when exposed to air and moisture. Same thing with these. These all retain metallic luster. Silver can get attacked, tarnish, oxidize. So silver is not as good and copper is not as good. But these metals are very good at resisting oxidation. But these are all the coinage metals. The coinage metals are called the Nobel metals. These gases are called the Nobel gases. The Nobel gases are unreactive. The Nobel metals are unreactive. Here. So it's kind of a similar thing. However, these metals over here are highly reactive. And so this is +1, +2. Scandium and yttrium are +3 always. Titanium is +4, +3, +2, +1. Vanadium +5, +4, +3, +2, +1, etc. These guys over here, they can either lose. For example, chlorine can lose up to how many? These guys can lose, so chlorine can lose up to how many? 7. And in perchlorate, how many has it lost? 7. And so chlorine's very unhappy losing 7 electrons. Perchlorate Pepcon explosion in Nevada shows you how unhappy the chlorine is in +7. You see the magnitude of that explosion? It's very unhappy. Because ammonium, you don't think of ammonium as being, you can buy ammonium cleaners at the supermarket. You don't really think of those as being terribly reactive, or highly flammable. But ammonium, when combined with perchlorate, is nasty stuff. And so it could lose up to 7. It doesn't have to lose up to 7. Chlorate only loses 5. Chlorite, hypochlorite, well, they lose different degrees. So losing 7 is losing a lot. It's going to make it very, very unhappy. How many can it gain? Chlorine can gain 1. And do you see, if it loses 7, it'll have 10, like neon. Chlorine is 17. If it gains 1, it'll have 18, like argon. And these guys are stable. And so these are patterns. Well, you know, where did the theory come about? Where did the theory come about for chemistry? Came from observations. These are the observations that people have to hypothesize what's going on. You know, like you were saying, there's got to be something going on with the structure. There is something going on with the structure. And so what we got to do is we got to figure out what is going on with the structure that leads to these types of properties. What is going on with these structures is going to be discussed in chapter 11, 9, 10, chapter 11. Chapter 11 deals with quantum mechanics. And so we're almost there. Maybe it'd be, maybe it'd be best just to start off with the theory, but the theory again is hard. And the theory came from observations, so we're just doing it more historically. Well, okay, so we have strong reducer, magnesium. What is oxygen? Okay, let's talk about the metathesis. Are there metathesis properties for oxygen? No. There are no metathesis. So no reaction with metathesis. Are there acid-base properties for oxygen? Is oxygen a good H donor? H atom donor? No. Is it a good H acceptor? No. H plus. And so there's no Bronsted acid-base properties. However, there's Lewis acid-base. One of the most important Lewis acid-base reactions occurs in your body, and that's with hemoglobin. Hemoglobin is a Lewis acid, and oxygen is a Lewis base. And we have a Lewis acid-base reaction when oxygen combines with heme in hemoglobin. Unfortunately, there are more powerful Lewis bases out there. One of the most powerful Lewis bases is carbon monoxide. So if there's a competition between carbon monoxide and oxygen for hemoglobin, carbon monoxide wins because it's a much stronger Lewis base. Cyanide. Cyanide is a very powerful Lewis base. And so cyanide can attack hemoglobin. When cyanide and carbon monoxide attack hemoglobin, that's it. Hemoglobin won't accept oxygen. Well, anyway, getting back to this. So essentially there's no metathesis, no Bronsted acid base. That leaves redox. Now as far as redox goes, is oxygen on the oxidizer side or the reducer side? It's on the oxidizer side. Is it a strong, moderate, or weak? It's a strong oxidizer, so we're set. And so what happens is magnesium is a reducer. What do reducers do? They lose electrons. I don't think we need to look at the chart. This is in the chart. Magnesium will go to magnesium 2 plus 2 electrons, except I'm reading it backwards. The chart has it the opposite way, but I can reverse it easily because I have magnesium here instead of magnesium ion. And so magnesium is going to lose 2 electrons there. And then the oxygen is going to gain. There are 2 ways we can do oxygen gaining electrons. We could do it like your book does it, an oxygen atom plus 2 electrons. So what we have to have is this. I'm going to have like an O2 here, and the O2 is going to dissociate into 2 O's. And then I'll take one of those O's and bring it over here. And then one of those O's will gain an electron to form oxide. And so then we'll just combine this. When we combine this, we got to make sure everything's balanced. So in order to make everything balanced, it's going to be like this. I'm going to have magnesium like this, plus an O2, because each magnesium needs just 1. And so magnesium is solid, O2 is a gas. I'm going to form MgO. Magnesium ions and oxide ions combined form magnesium oxide, which is a solid. So this is a redox reaction. This is what we call an element plus element combination reaction. Element plus element. when we have an element plus element, we just use the periodic table. How many electrons does one lose? How many electrons does one gain? And then figure it out based on that. Some of these are multiple, so it's hard to predict. So for example, copper. Copper can lose 1 or 2 when reacting with oxygen. And so if copper loses 1, then we form this. This is called what? Cu2O is called well, Cu2 is brown. So when you have a shiny new penny, the shiny new penny doesn't stay shiny forever. Eventually it's going to turn brown. And then over a longer period of time, it'll start to turn black. The black is CuO. So the brown, this is called copper 1 oxide. The black is called copper 2 oxide. And so it could form multiple products depending on how many electrons it loses. You know, some things can lose variable amounts of electrons, so we can form variable amounts of product. Well, let's say I don't want any black, I just want brown. Well, how can you do that? Well, you can't really stop it. You know, eventually it's going to oxidize. And so there are conditions you can change, you know. And so with products here, it's easy because magnesium only forms 2+. That's it. It's a fixed charge cation. We've memorized the charges. All right, now I have magnesium oxide. And so what I'm going to do is I'm going to take this white magnesium oxide, and then I'm going to add water to this here. Okay, so if I take my white solid magnesium oxide and add water to it, does anything happen? Okay, and so this is reaction number 2. The ash from above is mixed with water. So I'll take this, the ash, and mix it with water. Now, is magnesium oxide soluble? Is rust soluble? No. Oxides are not soluble unless they're group 1 or ammonium. That's not on the list, but it would be great if it were, because then you can wash off the rust off it rather than sand it off or eat it off with some chemical. And so I mixed it there. But it turns out a reaction's happening, a little bit of reaction's happening here with this. Now, what is the reaction? Is it metathesis? Sometimes people like to think of this as metathesis. One way of thinking about this as metathesis is like this. It's technically, metathesis deals with ions, and water's not an ionic compound, but we might think of it as an ionic compound. So we got magnesium 2, but these magnesium 2s aren't free. These magnesium 2s are stuck in the solid state. That means they have no translational motion. Plus the oxides are stuck in the solid state. They have no translational motion. They're stuck. And so one way of thinking about water is like this. Water is the H plus and the OH minus. And so this is one way of thinking about it. So what would form here? What would your guess be? What ion combinations look good to you? How about magnesium with hydroxide? Does that look good? Hydroxides are all soluble or insoluble. Insoluble except for group 1.
Group 1 ammonium, calcium, strontium, barium.
Yeah, group 1 ammonium, calcium, strontium, barium. Are you guys going through the solubility rules every day? Or are you going to cram them in the night before? Yeah, try to do it every day. You know, however, you try different methods too, if you want, but try to get them down, and so that they become more automatic. And so magnesium hydroxide is insoluble. What's the formula for magnesium hydroxide? MgOH2, and this is going to be a solid. That's a favorable ion combination, right? And do hydrogen ions like oxide ions? Yeah. What forms? When hydrogen ions combine with oxide ions, we're going to form. Well, let's balance it out. Well, we're going to do two waters here. Yeah. So it'll form H2O liquid. And so we'll end up with this. MgO solid plus 2 H2O liquids yields MgOH2 solid plus H2O liquid. Well, we got H2O liquid here. We got 2 here. Let's get rid of those. This is spectator. Another one. And so just one of these will form hydroxide. All right, so this is kind of a metathesis reaction, sort of. You know, but it's not an easy one. It's kind of complicated. Then we have acid-base. Well, acid-base, I know something about oxide. What do you know about oxide? Oxide stands out in acid-base reactions. Why? Is it chart? Name all the strong bases you can from memory. From memory. Name all the strong bases that you can from memory. NH2 minus, amide, yeah, good. Hydroxide, good. O2 minus, which is called oxide in sulfide. The big ones are hydroxide, oxide, sulfide. And so oxide is a strong base. But normally, does that mean rust is a strong base? If oxide is a strong base, is rust a strong base? Fe2O3. No. So what we say is this. This is not a strong base, not a strong base. So what we say is this. We say that the soluble oxides are strong bases. So if I had sodium oxide, strong base. Potassium oxide, strong base. You know, group 1 oxides are going to be strong bases. But that doesn't mean it can't react as a base. Magnesium oxide can react as a base. It's just, the problem is that the oxide's locked up in the solid state, so it's going to be less reactive. When the oxide is trapped in the lattice, it's not free to react. And so this is why I'm going to separate the ions, but I'm going to have this. You know, this is a lattice structure. This lattice consists of magnesium ions and oxide ions locked. Now those oxide ions are locked in the lattice, meaning they're less reactive, but they still can react on the surface. They still can react on the surface. So you can see here, do you see I have most of my oxides still there. Right? But that doesn't mean it didn't react. How do I know this reacted? I'll tell you how I know that this reacted. Okay, so the oxide can react. Now what is water? Water is special. Water is both an acid and a base. So here we have base. Magnesium's neutral. Water is an acid or base. In this case, it's the best acid around. And so the acid-base reaction we're going to have is oxide that's locked in the solid lattice reacting with water. So it's going to be less reactive, but it still can react. And when oxide reacts with water, what do we form? Not hydronium. Hydroxide. We're going to form 2 hydroxides. Now, how do I know if any reaction occurred? I know phenolphthalein. You know what phenolphthalein detects? Phenolphthalein detects hydroxide. If there's hydroxide present, it's going to change color to pink. And so what I'm going to do is I'm going to take a drop of phenolphthalein, which is just a dye. It's not that hazardous. Actually, this is not that hazardous either. But I'm going to put a drop of phenolphthalein in here, and let's look at what happens to the color. Phenolphthaleine's colorless. I put a drop in here. And let's see what happens. Nothing. Nothing happened, meaning it's not that reactive, but we have to be careful because sometimes nothing happens because I didn't mix it well enough. Sometimes nothing happens because maybe my phenolphthalaine's not good. Let me just check my phenolphthalein here really quick, just to make sure. I'll take some base here. Bases do have hydroxide present in them. There it goes. And so I'm not getting much reaction here at all. In fact, I don't see any evidence. But I wonder, it could be my water too. Let me check something really quick. Did I use DI water or did I use tap water? We have two types of water here. This one's tap, this is DI. I was supposed to use DI water. Our DI, it's not distilled. Distilled water is kind of expensive. So it's similar to distilled, but it's a much cheaper version. But it doesn't have the same purity. Alright, so we'll try to get this to react. There's not going to be much reaction because remember the oxide's locked in the lattice. So what I'm going to do is I'm just going to take the remaining product here and put that in here, mix it up. Alright, now I'm going to add my drop of phenolphthalein to this. And still nothing. I don't see any. And so it could be no reaction that's happening here with this.
Well, it says on the instructions, it says to only add a few drops of distilled water.
Yeah, the instructions say only add a few drops. Oh, do you see? Maybe I added too much. Can you see it? Yeah, the pink. I probably added too much, which means it's too dilute. And so let's try that here and see. Hey. All right, we're going to add another drop of phenolphthalein. See. All right, now can you see? Do you see it now? Yeah. So that was a concentration. One, this doesn't. Two, sometimes you have to give these reactions time. Sometimes these reactions don't happen so quickly. Especially this. Solids tend to react very slow compared to liquids and gases, which react a lot faster. But now, do you see more pink color coming? Yeah. All right, so there we go. And so when we have oxide that's locked in a lattice, it's not going to be reactive. I mean, if the oxide was free, we would have gotten pink right away. And not only that, we didn't generate that much. Because we aren't going to generate that much because the hydroxide also is not free. The hydroxide is locked in a solid lattice as well. And so that can't freely react with ammonia. I mean, with the phenolphthalein. When we compare that to this, let me just show you. When we have when we have hydroxide that's free, not locked in the lattice, look how quick this works. This is phenolphthalein, 1 drop of phenolphthalein. You see that? It's free. And so this is well, anyway.
That's what,
Uh-huh.
what is the equation for chemical equation for
Phenolphthalein and hydroxide. What's the chemical equation?
yeah.
The phenolphthalein and hydroxide is. Do they want that equation?
No, I'm just curious.
All right. Phenolphthalein is organic acid, and its formula is kind of complicated. And so what chemists tend to do is they just write it like this. And so this would be H plus, and this would be the phenolphthalein anion, which would be negative. Now the phenolphthalein anion, when combined with H plus, is colorless. What happens is this: when I add hydroxide, the hydroxide loves hydrogen ion. That's a favorable ion combination. And so what results is this: rather than having H-phenolphthalein, this is a weak acid. Weak acids stay together. And so this weak acid is colorless. When the hydroxide attacks, it's going to pull the hydrogen off the phenolphthalein, and we're going to be left with phenolphthalein, the anion, alone, and water. And when phenolphthalein is like this, then it's pink in color. And so when phenolphthalein has the H plus attached, it's colorless. When the H plus becomes detached, it changes color. The reason is because it changes the electronic, what we call the electronic environment or electronic structure around the molecule. If you want the formula for phenolphthalein, show it to you. Here.
I have a question. So the ash that was produced on the burning of magnesium is magnesium oxide, right?
The ash that's produced is magnesium oxide, the white ash. These you want to write in your notebook, your lab notebook. The first series of experiments I'm going to do, the next series you'll do. But we're going to take a break right after I just show you what phenolphthalein is. And then we'll take a break. And so magnesium is burned in air. The observation is the silver metal magnesium combusts from a white flame, white hot flame. An equation I wrote on the board. Number 2, the ash from above is mixed with water and tested with indicators. You don't have to write the equation with the indicators.
You just have to do the magnesium oxide
Yeah.
plus water.
All right, this is it here, except this is written in a shorthand notation. This shorthand notation is just quicker than writing it all out. But this is the structure of its molecule. It's a solid acid. We have solid acids, liquid acids. Acetic acid is liquid in pure form, and gaseous acids. This happens to be a solid acid, like citric acid or those. This is its systematic name. It's called 3,3-bis-4-hydroxyphenyl 2-benzofuran 1,3H1. There are other names for this: 3,3-bis-4-hydroxyphenyl isobenzofuran 1. These names are pain, so everybody calls it phenolphthalein. It's a lot easier. And when you write out the ion formula, it's a pain, so everybody just writes phenyl or fen. Phenyl's for something else, but fen maybe, or something comparable. It may not look like an acid to you, but these are. Phenolphthalein turns out to be a a diprotic acid. In one form, it could be a triprotic acid here. These are all phenolphthalein as acid. This is H2IN. IN is the generic. We don't want to write out the whole formula, so they just write IN. IN just stands for indicator. And so here it's a diprotic acid, and when the hydrogens are stripped off, take a look at what happens to color. It's colorless with the hydrogens attached. When the hydrogens are stripped off, it becomes pink to fuchsia. Okay, now, if you get hydroxide in there and you get lots of hydroxide, it goes back to colorless. And so it's an orange in very low pHs, very acidic. Low pH is very acidic. Very acidic, it's orange. You can actually throw another hydrogen on there because this is what we call amphoteric. Phenolphthalein can act as an acid and it can act as a base. If phenolphthalein acts as a base, it accepts another hydrogen ion, which turns it orange. It would act as but it has to be very acidic for that to happen. And so this is all the structural stuff. And if you want to write out the equations, it's a bit of a pain if you want to do it properly, you know. And so this is why I'm going to skip it. Okay, let's take a break and then we'll start again. Oh, now you see some of these reactions, you just have to give them time or concentrate them. You know, the more concentrated things are, the quicker they'll react. And this one wasn't because the oxides are locked in the lattice. Uh-huh.
What was the equation for this one again?
Yields MgO, and then balance it.